Welcome back, Math 1910, Calculus 1. We are starting Chapter 5, Section 1. We're going to learn a little bit about natural log functions. You may have learned about log functions in the past, dealing with log base 10, but we're going to deal with natural log functions, or log naturel. It's the ln button that's on your calculator. So we're going to learn, when to apply the natural log function, what the base of the natural log function is. It's going to be e. Okay, and how to take derivatives of natural log functions, and when we can apply those. When is it appropriate to use a natural log to take a derivative? Well, the first thing is understanding different derivatives that we can't take, or if we look at a power rule or things like that, right? We cannot apply it to n equals -1 in this case, right? If we have the integral from x to the n dx, all right. If we apply the general power rule to that, if n is -1, we cannot do that. Okay, in the past we've had to maybe rewrite something as an exponent or things like that. But in this case, we have an easier way when we start taking the natural log function. Okay, so it's a transcendental, okay, or it's non-transcendental. Sorry, if we go through this, it's neither algebraic nor trigonometric. So those are, when we talk about early transcendentals and things like that. Transcendental is anything that's like not algebraic based for the most part. So natural log here, all right, is a transcendental function as we go through here. So this is kind of our first step at taking a look at those type of functions. All right, so if we look at this, all right, if we take a look at the definition of the natural log function, okay, it's natural log of x. So you pronounce that ln of x is natural log of x. In Europe, you're going to get log natural or things like that. So we that's why it's ln, because technically they say log natural versus natural log. For us over here, we've always called it natural log, but that's why it's ln instead of nl in that sort of scenario. All right, but it's the integral from 1 to x of 1 over t dt. So notice that 1 over t is representative of if we have like a negative exponent or things like that. So we can do it for all positive real numbers when we do this, as long as x is greater than 0. Okay, so we're going to see here soon that if natural log of x is positive when x is greater than 1, and it's going to be negative when x is between 1 and 0. We can see this a little bit better here if we actually take a look at the graph of 1 over x here. Okay, so if we take a look at this, you can kind of see what the slope field is doing. So this is the graph of y equals natural log of x. So you can plug this into your calculator as well. So hit the ln, or hit y equals first, hit the ln of x button on your calculator, okay, and then you can just hit zoom 6 and it'll put it in a standard viewing window for you to take a look at. So you'll see what the graph of the natural log curve looks like. Okay, understanding some other properties of natural log. All right, the domain for the natural log is from 0 to infinity. Okay, we saw that on the graph, so I'll step back. If we take a look at the graph here, the domain, right, the x values are from 0 to infinity. And if we take a look at the range is negative infinity to positive infinity. So just some basic properties of natural log here. Okay, it's continuous, it's increasing, and it's 1 to 1, right? Remember, 1x input equals 1y output. And the graph is always considered concave downward for its entirety. So if you take a look at the graph, right, and even if you put it in your calculator, right, you type in natural log of x and you hit, zoom standard puts it in the 10 by 10 window, but you can, zoom out from there and you'll see, exactly what the properties look like. And you can see the range is negative infinity to positive infinity, the domain is 0 to infinity, and so on and so forth. All right, properties of logs. These might be familiar to some of you guys that used log base 10, all right, in some of your other classes. If you took physics or things like that, log base 10, you'll see kind of where that comes into play. All right, but Theorem 5.2, they're log properties, and everything that we're going to deal with in calculus, for the most part, is all going to be natural logs. You're not going to be doing log base 10. All right, but the rules are the same. Okay, the rules are the same whether you're using log or natural log. So for us, natural log of 1 is 0. Natural log of a times b, all right, is going to be natural log of a plus natural log of b. You're going to learn to rewrite logarithms. And if you did logs before, you did the same sort of thing. But if you understand power rules of exponents, you're going to understand log rules. All right, and so when I say that, things with the same base, right? If we had like x squared, right, times x squared, we would add the exponents. That's kind of essentially what you're doing here. You know, and if we had division, right, x squared, you know, divided by x to the fourth or something like that, we would subtract the exponents, and then when we had a power to a power, we would multiply. So it's kind of understanding the exponent rules. But if we go through these, natural log of 1 is 0. Natural log of a times b, all right, we can rewrite that as natural log of a plus natural log of b. If we have natural log of a to the n, so a to a power or exponent, right? That exponent comes down in front. Very, very important rule here for us to simplify logs. So that exponent always comes down in front. So it becomes n natural log of a here. And then if we have division or quotient going on here, we have natural log of a divided by b. We can rewrite that as natural log of a minus natural log of b. So very helpful. I need you to make sure that you know and understand these properties, memorize them, learn them. You're going to have to apply them throughout. So if we take a look here, right, here's an example. This is the quotient one, right? We have natural log of 10 divided by natural log of 9. We can rewrite that as natural log of 10 minus natural log of 9 when we do this. And this will help us later on when we have to start doing derivatives and integrals. So that's mainly why we're understanding and going through the different properties here and learning how to rewrite them. So this one, you know, first of all, we see natural log of the square root of 3x plus 2. So first instinct, rewrite that square root sign as an exponent of 1/2 when we do that. So we get natural log of 3x plus 2 to the 1/2 power. Then we can bring that 1/2 down in front from the properties we had on the previous page. So now that we have that exponent, that's how we learn to solve for exponents and things like that using natural logs. So we can bring that exponent down in front. So it becomes 1/2 times the natural log of 3x plus 2. All right, so just rewriting logs here. Now, different version of the quotient. I mean, we're still going to apply the quotient, but notice that we have 6 times x. All right, so we're going to have a product piece in there, and that 6 times x is being divided by 5. So in this case, undo the quotient piece first. So you're going to rewrite it as natural log of 6x minus natural log of 5. Then we are going to rewrite that natural log of 6x as natural log of 6 plus natural log of x minus natural log of 5. So everything that we're doing here in this example, this is called expanding logarithm expressions. So we're expanding them. We're making them, you know, bigger, or spreading them out. We're undoing some properties. Or technically, I guess, applying the properties as we go through it. Okay, so we're expanding them. Where they were condensed, we're going to expand them out and make them longer, which is going to help us in solving for x or things like that. Okay, so if we take a look at this one, we have the natural log of x squared plus 3 quantity squared divided by x times the cube root of x squared plus 1. Okay, so we got to be careful here. You know, undo the quotient piece first. Okay, this is going to expand rather lengthy here. If we take a look at this, we have one big quotient. All right, so we're going to undo the quotient first. So we're going to get natural log of x squared plus 3 quantity squared minus natural log of x times the cube root of x squared plus 1. Okay, so we've rewritten that as subtraction. Now we need to start doing some other pieces here. We notice that we have that square root sign. That's going to be a 1/2 power. All right, and we have a few other rules to apply here. So on the first one, we can bring that exponent that's a 2 down in front. So we're bringing the 2 down. So we had 2 natural log of x squared plus 3, right? And then on the other one, notice it was x times the cube root of something. We rewrote that cube root as 1/3. I think a few seconds ago I might have said square root, but it's the cube root. So we're rewriting x squared plus 1 to the 1/3 power. And then since it's x times that root, that cube root, that turns into a plus. Okay, so since it's x times the cube root of x squared plus 1, that becomes the natural log of x plus the natural log of x squared plus 1 to the 1/3. So rewrite the root and then apply the product piece that's going on there so that you can separate everything out. All right. Then lastly, distribute the negative sign through. All right. So that negative okay, that's outside the brackets, it changes the sign of the other two functions as you go through there. So you can see how we end up with negative natural log of x minus natural log of x squared plus 1 to the 1/3. Okay, so that's changing those signs. Then when we do that, we've got to be able to bring that 1/3 down in front. Okay, so you remember this is step-by-step methodical. If you can see most of this in your head as you go through the problem, that's completely fine. All right, but we get 2 natural log of x squared plus 3 minus natural log of x minus that 1/3, that exponent comes down in front, natural log of x squared plus 1. So we've completely, expanded this as much as we can. All right, so let's take a look, just, some graphic properties in here. If we take a look, we have, what does the natural log of x squared look like? Well, if we look at figure 5.4 here, we have g of x, all right, which is 2 natural log of x, but look at how it compares to natural log of x squared. The natural log of x squared will handle all of the negative values. So you just got to make sure that, the domain of natural log of x squared is all real numbers, and the domain of g of x is all positive real numbers. So you just have to make sure that you understand, how those two relate when we rewrite them. All right, so notice that f of x is our original function, g of x is us rewriting using the power properties or power rules. Okay, so back when you've potentially looked at logs before in physics, or maybe your math class, maybe end of algebra 2 or something along those lines, when you looked at logs, right? You did log base 10. That's the other button on your calculator that says log. It has a base 10. Okay, so I mean it's about understanding logs. So what power can I put on the base, which is log base 10, to get 10 as a result? And I'll probably go over this a little bit more on the board in class for live lecture, but log base 10. So if I go 10 to the first power, I get 10. So that's kind of another way I want you guys to think of, how to solve these. Well, that's for log base 10 functions. We're doing natural log functions. So the base for our natural log function is e. Notice you have that e to the x function for exponential growth. All right, but that base e is a specific number. Okay, that specific number, it's irrational, it goes on forever, but it's the 2.71828, as you can see. Okay, it's on your calculator. Notice you have the natural log of x button, and then above that you have the e to the x button. So, you're interchanging bases. So what you need to understand, right, is that if you take the natural log of e to the first, you will get 1, because e is the base of natural log. Okay, so very, very important that we understand that e is the base for natural log, just like 10 is the base for our regular log functions. Okay, so it's important for us that we know, if we look at this, the natural log of e is the same thing as going from 1 to e of 1 over t dt, and it equals 1. Okay, so very, very important, and that we can use this to evaluate a whole bunch of different natural logs, okay, with other numbers. And we can create a table here, so we can kind of see how everything, works out. If we have 1 over e cubed, 1 over e squared, 1 over e, and we can get what the actual answer is going to be. And I'll go over this about rewriting them in class later on. But if we look, if we take a look at this example, if we use the power property, right, we have natural log of e to the n. Well, that n comes down in front, right? So then I have n times the natural log of e, and we already know the natural log of e is 1, so it just ends up being n times 1. So this is going to be important for us when we learn how to actually, solve some exponential equations and things like that, without using a calculator. So very, very important. So, a table is convenient for us to see, but we can do these in a calculator as well. So, for us, natural log of 2, if you hit ln of 2 in your calculator, you're going to get 0.693. Okay, so that means, what power can I put on e to get an answer of 2? If I take e to the 0.693 power, I'll get approximately 2. And the reason it'll be off is because you need like multiple decimal places, more than just 3 decimal places, to get more of the exact answer. But you can put this in your calculator, right? I can hit natural log of 32, hit enter on my calculator, I'll get 3.466. But, you know, conversely, I can say e to what power gives me 32? E to the 3.466 power will approximately give me an answer of 32. So I want you to think both directions there. Okay, and we're able to handle negative values, right? So natural log of 0.1, if you hit that in your calculator, you're going to get negative 2.303. If I take e to the negative 2.303, I'll get 0.1. So I want you to understand how to go back and forth between natural log and e when we solve this. All right, but importantly, I'm going to throw some calculus into the game here. All right, so a good way for us to do this is understanding how to rewrite natural log of x. The derivative d dx with respect to x of the natural log of x is going to be 1 over x as long as x is greater than 0. All right, we can't handle the negatives in this particular case here. Now, another way, say we have a more complicated function than x, we can do u substitution. And we've been doing u substitution throughout. So in chapter 2 when we did derivatives, in chapter 4 when we did integrals, things like that, same kind of concept with u substitution. So we can take the derivative with respect to x of the natural log of u becomes 1 over u times du. So we can really write this as du over u or u prime over u. So that's if we use u substitution, it becomes sort of a chain rule type scenario for us as we evaluate that. So let's take a look at an example here. We want to take the derivative with respect to x of the natural log of 2x. Okay, so we understand, right, that if we rewrite that and how that works out using our law properties. So I'm going to step back here. We can see that the derivative of natural log of x is 1 over x. Okay, but we have 2x, so we've got to make sure that we multiply by du. So this might be a u substitution. So generally when we choose u, all right, u is going to be the argument piece, like the 2x in this scenario. So we want to get it into u prime over u. So if you let u be 2x, you know that du is going to be 2. Okay, so the natural log of u, the derivative of the natural log of u is 1 over u times du. So that's what's shown here. Du is the same thing as u prime, right? Okay, so when we substitute that in, it becomes 2 over 2x, and then we simplify, all right, 2 over 2 becomes 1, so we end up getting 1 over x. As long as we let u equal 2x, right, we know that du equals 2 dx, all right, and then when we do our u substitution, everything works out. Let's do the next one here. We want to take the derivative with respect to x of the natural log of x squared plus 1. So you're going to let u be x squared plus 1. All right, so du is going to be 2x dx, all right, and then we do our substitution, so then we have to take the derivative of the natural log of u, okay, and we know the derivative of the natural log of u is du over u, or u prime over u. So once we've established, you know, what u and du are, we substitute them back in after we take the derivative, okay? So natural log function, you know, very easy for us to take the derivative of and then set things back in. So we know that du was 2x, all right, so we replace u prime with 2x, and we know that u was x squared plus 1. So very important that we understand that piece. All right, let's say we have the product rule here first. All right, that doesn't change from chapter 2. We want to take the derivative with respect to x of x natural log of x. So it's still first times the derivative of the second plus the second times the derivative of the first. Same product rule that we did in chapter 2, all right, for polynomials or things like that. All right, so you're going to take x times the derivative of natural log of x plus natural log of x times the derivative of x. All right, so still product rule. So we end up getting x times 1 over x, right? Because the derivative of natural log of x is 1 over x, plus natural log of x times the derivative of x is just 1. Okay, so we end up with our final answer is 1 plus natural log of x, right? Because x times 1 over x cancels and becomes 1. So Very simple, but we have to make sure, you know, the quotient rule still applies, low D high minus high D low all over low low, or, you know, sometimes it's advantageous to rewrite it first before we take the derivative as well. Let's take a look at this one. All right, we have the derivative with respect to x of the natural log of x cubed. So, still, okay, we have to make sure that we understand this is a chain rule problem. Chain rule problem first. So the derivative of the outside times the derivative of the inside. So we're going to do the power rule piece first, right? So the 3 comes down in front, okay, and then we do 3 minus 1, which is 2. So that's where the 3 natural log of x2 squared comes from. Then we have to take the derivative of the inside. The inside is natural log of x. So when we take the derivative of the natural log of x, we get 1 over x. So this simplifies down into 3 natural log of x quantity squared, okay, times 1 over x. So make sure that you're understanding that's a chain rule problem. All right, there's an exponent. All right, there's a quantity and an exponent. So the derivative of the outside, which is the power rule, times the derivative of the inside, which in this case is just the derivative of natural log. All right, so let's work through this one. All right, this is something, you know, you can't really choose a good use substitution or things. I mean, you can maybe work through it that way. It just can be, you know, a bit more painstaking for you guys, you know, to kind of work through this. Now, we want to find the derivative of y equals the quantity of x minus 2 squared divided by the square root of x squared plus 1. So, you know, you gotta do your due diligence here and change your approach a little bit. You know, are you gonna want to throw a quotient rule at this? Okay, it might get kind of sloppy and messy if you do a quotient rule with this. But can we throw natural log at this right away? No, because there's no natural log yet. But for us, it's much easier. We can apply natural log as long as we follow, you know, a basic rule of algebra. What you do to one side, you must do to the other side. So I can make this become a natural log problem. So it's a little bit easier for us to take the derivative of. The way I can do this is I can multiply both sides of this equation by natural log. And this is how we have to learn how to solve doing logarithmic differentiation. We're going to multiply both sides of this equation by natural log. What you do to one side, you must do to the other side. So when we do that, okay, then we're going to solve for y prime, or dy. All right, so when we do this, okay, it's going to be very important as we do this. So if we write the original equation out, and we're going to multiply both sides by natural log of x, okay, basic rule of algebra that we can apply. So for us, it makes more sense because we can take the derivative of this function with a natural log a little bit easier, and you'll see as we expand things out. So once we do that, before we start taking the derivative, rewrite the natural log. I'm going to step back a slide. Look at the bottom here. If we take the natural log of both sides, all right, then we apply the quotient rule, right, for logs. So now when we do that, we no longer have a denominator that we have to worry about. Okay, we can just have a subtraction. Also notice the steps here. The denominator here was x, the square root of x squared plus 1. Notice when you apply the properties of log, you rewrite that as x squared plus 1 to the 1/2, and that 1/2 comes down in front. Notice the exponent on x minus 2 is 2. That also comes down in front when we've skipped ahead here in the slide. So a couple of properties, we've expanded this out. Now we have the natural log of y equals 2 times the natural log of x minus 2 minus 1/2 times the natural log of x squared plus 1. Now we're able to take the derivative of the function. All right, and you got to make sure that you're taking things correctly on the left-hand side as well. All right, you have to know, oh, I have the natural log of y. I got to take the derivative of the natural log of y. Well, that just becomes what? 1 over y times dy. So that's where we get our y prime in that we're looking for. And then, all right, the derivative of 2 natural log of x minus 2 becomes 2 times 1 over x minus 2. Okay, just doing our derivative of the natural log. Very simple. Chain rule right. And then we have minus 1/2. times 2x divided by x squared plus 1. So let's walk through that one because, u is our x squared plus 1, right? So we know the natural log of u is du over u. So we know that the derivative of the inside stuff, the derivative of x squared is 2x. So that's where that came from. All right, and the derivative of of u, right, is 1 over u, which gave us the x squared plus 1. So that's how that works out. We're just using the derivatives of natural logs as we do this, okay? Then we have to solve this equation, okay, for y prime when we do this. So when we do the algebra here and expand and simplify, all right, and you place, you solve for y prime. You're not solving for y prime over y, you're solving for y prime. So you're going to have to go back, and if we look at the original equation of what y is, that's going to be substituted back in for us to solve. All right. So to go through, I'm not going to spend a lot of time going through the algebra on this. You should be able to do that, but you're solving for y prime. So that means you got to multiply both sides by y first, and then replace y with what the original function is when you go through there. Okay. So as we simplify down, okay, it goes through here. We replace y with what it was originally. Okay. And then that's going to help us simplify as well. So if I go back up to the other step where I was telling you to simplify, make sure you find a common denominator. So a common denominator that's easiest to choose is, multiplying everything, together, so that you ended up with x minus 2 times x squared plus 1. And figure out what's missing. You guys should know the algebra on that step though. All right. Lastly though, we're solving for y prime. We multiply both sides by y. Then we have to rewrite y with what it was originally. So that x squared minus 2 quantity squared divided by the square root of x squared plus 1. That was our original y from, I'm going to step back a slide here, the problem. You can see the top, right? Y equals. So we're replacing that in. All right, and then a little bit more algebra goes a long way here. Distribute some things. We can see that the x minus 2 squared in the numerator can cancel with the x minus 2 in the denominator. All right, so we're left with an x minus 2 in the numerator. And then if you rewrite x squared plus 1, the square root of x squared plus 1, if you rewrite that as x squared plus 1 to the 1/2 power, you can multiply that times the x squared plus 1, all right, and then add the exponents. So that's why it becomes x squared plus 1 to the 3/2 power, all right, when you're working through that problem. All right, and I'll rework one similar to this on the board, again, during live lecture in class. All right. Next, all right, Theorem 5.4. If we have the derivative involving an absolute value function, all right, now we can say, oh, we can turn it into just taking the natural log of the absolute value of u. Okay, so if we, as long as you use a differentiable function, all right, and now we can take the derivative of that function using natural log of absolute value. Okay, so it helps us out here when we have absolute value functions. All right, because remember, those are a little bit harder because we got to rewrite those as two functions sometimes to work through them. So if we have the natural log of the absolute value of a function, we can just rewrite it as du over u, or u prime over u. Let's take an example here. We want to find the derivative of the natural log of cosine of x. So let u be cosine, right? U is cosine, du is the derivative of cosine, right, which is minus the sine of x times dx. Okay, then we just simply rewrite our natural log. So as long as we choose u and everything correctly, all right, we're able to work through this piece here. So as long as u is cosine, like I said, all right, du is minus the sine, and when we replace it, we'll write the natural log of x. When we take the derivative is just 1 over x, right, times du, so we end up with negative sine of x divided by cosine of x. Just doing our simple u substitution there. All right, so we end up taking, the natural log of u and taking the derivative of that. So it's 1 over u times du, so that's why we get negative sine of x, that's du, and then the 1 over u is 1 over cosine of x. So there's where we end up with as our solution. Alright, and like I said, I'll do more of these in class. I think as you do more of the homework problems, you'll find that these are relatively easier than you think. You just kind of got to get the practice down, but they're not as bad as you think, especially doing the rewriting. Once you learn how to do the rewriting fluently, you'll be doing alright. But as usual, guys, email me with any questions. Let me know if we need to Zoom meet or team meet or anything else like that. Else, guys, have a great day. I'll see you in class.